In this video of Neural Breakdown, we will be learning about language models. Specifically, we will be starting from the very scratch and then build up a language model brick by brick, module by module, and teach it to generate any sequence. And along the way, we will be learning about all of the major building blocks that you must know to build a language model on your own, from cosine similarities to attention scores to context vectors to transformer blocks to causal mask attention and training on the task of next word prediction. If you watched my 3-part attention series, that was a good introduction to the theory and the intuition behind transformer models and language models. In this video, we will be applying that theory into something practical and turn it into code and just see it all work in front of our eyes. And I'm going to walk you through every line of code, explain to you everything, and by the time you've finished watching this video, you'll have a great understanding of everything about causal language modeling. So at the heart of large language models like ChatGPT and all lies transformer architecture, specifically a decoder transformer architecture. At the heart of this transformer decoder architecture lies the concept of attention, and at the heart of attention lies the concept of semantic similarities. So let's start from the very basic and see how semantic similarities can be captured between two vectors. So let's say you have two items, item 1 and item 2, and let's say you have acquired embeddings for these items. For now, just imagine these numbers to numerically represent something about item 1 and these numbers to numerically represent something about item 2. Now it doesn't matter what these numbers are, it's just a contrived example that I'm showing to demonstrate a point. So here I am plotting how these numbers sort of look like, and if you see, you'll find where the values of item 1 and item 2 are similar. At the first point, they are quite similar. Item 1 was 1, item 2 was 2. And the last point as well, it's quite similar. They're both 4. In this third point, they're also similar because they're both negative, and one is -2, one is -3. In the second point, they are not similar because they are facing opposite directions. So what will happen if we just multiplied these two vectors element by element? Well, it's going to give us a new vector. And what if we plotted that vector? Well, now you can see wherever the numbers are positive were places where both the numbers had the same polarity. If they were both negative, the output if they were both negative, the output is positive, and if they were both positive, the output is also positive. Also, depending on how large the attributes themselves were, the height of this bar graph is also high. So for this one, you have 4 times 4, and that is 16. Now I'm going to explain why we did this product in a bit, but before that, we have to talk about the concept of vectorizing. Now suppose instead of one item 1, we have 3 items. And each of these 3 items have their own vector embeddings. So item 1 is 1, 2, -3, 4. Item 3 is actually the reverse of that. So -1, -2, 3, -4. And the second one is some arbitrary another number, another embedding basically. And you have the search embedding, which I've intentionally picked the same as the first embedding from the item. Now the reason I'm calling this search embeddings is because by the end of this little bit, we will be able to find which of these items from these embeddings have the highest similarity or semantic similarity with our search embedding. Now once again, let's do a product of item and search embeddings. So here, because we're doing a product, this the first shape is 3, 4 because you had 3 embeddings. The second shape is 1, 4 because you had like 1 search embedding, and the product is also 3 by 4. And if I show what the products sort of look like, you can basically see that we have element-wise multiplied the search embedding with item embedding for all 3 rows. So the product of 1 to -3, 4 and 1 to -4 is 1, 4, 9, 16, and the product with this third is -1, -4, -9, -16. So hopefully you're able to understand what exactly is happening under the hood when we are doing this product. And here I've also plotted the embedding values and the product values to show what they look like. And you can see that this green bar basically shows the product of those 2 embedding values. And you can see that for item 1, they all have high values. And with item 3, they all have negative values. And for the second item, it's somewhere in between. Now, what happens if we did a column-wise sum of the products? When we do a sum along the columns, we are basically adding up 1, 4, 9, and 16. and that gives us minus 30. And summing up minus 1, minus 4, minus 9, minus 16 gives us minus 30. So what we're basically doing is that we are adding all of these green bars together into one large green bar, and depending on how many values where the attributes of the two vectors, the search embedding and the item embedding, were similar, you will have a higher overall sum of products, right? Now the fun part of this entire thing we did is that this entire element-wise product and the sum could just be written in one line. We can use the matrix multiplication operation from NumPy, which basically does a matrix multiplication, as you might have guessed, between item embeddings and the transpose of search embeddings. Now, if you remember your math class, you remember that when we do matrix multiplications between two matrices, the second dimension of the first matrix and the first dimension of the second matrix must be equal. So in this case, it's 4. The 4, if you remember, is basically the number of values in the embedding. So basically, to do this, you must ensure that the size of the embeddings of your items and the size of the embeddings of your search embeddings are the same. And next, after we do this matrix multiplication, the final output is going to be the first dimension of the first matrix and the second dimension of the second matrix. So it's going to be an output of shape 3, 1, and lo and behold, that's what the shape is. Matrix multiplication works. Now the fun thing about matrix multiplication with NumPy and these vectorization libraries like Pytorch, as we will also soon see, is that not only can you have multiple items when you're doing this matmul operation, you can also have multiple search embeddings. So if I have 3 item embeddings as I had before, but now I have 2 search embeddings, and if I run my np.matmul again, you'll now see there are 2 of these semantic similarity scores. The first one is again 1, 2, minus 3, 4, and 1, 2, minus 3, 4. So this particular cell is the similarity score of this vector and that vector. And this 30 is the similarity score between minus 1, minus 2, 3, minus 4, and this guy. So hopefully that sort of explains what goes on when we have multiple search queries going against multiple item embeddings. So you don't have to write some for loop to do this. You can just do np.matmul, or later we'll see torch.matmul, to achieve the same. And you can see that the shape would be 3, 2 for this operation. And so here, just to illustrate the point further, let's say you have number of items equals 10, number of queries equal to 3, and embedding size equal to 4. Now if we do our little matmul operation, what's going to be the product shape? Well, it's going to be 10, 3, number of items, number of queries. Now the next thing I'm going to talk about is, again, let's get back to this earlier example. Now here we have this 30, 18, minus 30. But what if instead of having some random similarity score, what if we wanted to see how similar they are relative to each other in a normalized scale? What percent is this query similar to this item compared to that item compared to that item? So we have to convert these 30, 18, and minus 30 into a probability distribution. And the way to do that is to use the softmax operation. What the softmax basically does is it converts any given input distribution into a probability distribution. And there, if you ran that, we can clearly see that the higher values got a higher score, the lower values got a lower score, and everything adds up to 1. So this guy and this guy adds up to 1, and all of these also add up to 1. So this is the concept of what an attention score basically is. You have some search embeddings and you have some item embeddings, which we will soon be calling as key embeddings, and we'll call these search embeddings as query embeddings. So you have a bunch of query embeddings and you have a bunch of key embeddings, and you want to find out for each query what is the attention score that query provides to all of the keys. So in this case, you're providing 99% attention between the first query to the first key. Now this is not exactly attention. We are still dealing with similarity scores or semantic similarity and all of that, but the concept of attention is pretty much the same. The only difference in case of attention is that we will learn the attention weights, meaning these embeddings, which are some arbitrary numbers that I just wrote out here. When we are going to train transformer models, these numbers are going to come from tokens or words. Those words and tokens will be converted into an embedding representation, and then we will do attention scores to find out how much attention each word is providing to all of the other words in the sentence. Now that's getting a bit ahead of myself, so I'm going to pause there. It's just a reminder that even if I'm telling you that this is an attention score, technically it's not. It's a similarity score, but when we are going to talk about attention, you'll find that they're basically the same thing. So the next thing I want to point out is that here you can see that the distribution is very skewed. Like, just because this number is very high, when you do softmax, it becomes more pronounced. So the high values get a very high score towards the number 1, and the low values get a very low score. But imagine if the numbers were much smaller in scale, like 1, -0.5, and 1.2. Like, these numbers are quite smaller in scale compared to these numbers, right? So if we did do the softmax of that, you'll indeed see that the distribution is quite well spread out. It's not heavily biased towards anything. But obviously, if we had the same numbers and just multiply everything by 10, suddenly you'll see that even if this number is 12 compared to that 10, after running softmax is 88% compared to only 11.9% for 10. When we train machine learning models, as we will soon be training them, it's very important to reduce this skew. We don't want over preference on one thing or the other, because what that will do is it will introduce variance into the training very early as the model begins to train, because the model's weight will start very randomly. And if we have these sort of skews in the initial parameterization, it's going to be very difficult to train the model. It's almost always better to have these numbers not be way too high, because the optimization space will become too sharp. And the problem is, if you have a small embedding size, this issue is much less predominant. Like, for example, I'm taking an embedding size of just 4. I have 4 items and 1 query, and I'm trying to print out the attention scores. And you can see that, okay, all of the numbers are pretty well balanced, because everything gets randomly initialized. And if I run it a couple of times, you'll see that almost never you see a very high sort of a skew. But if we had a very high embedding size, say 256, you'll suddenly see that there are going to be these sort of skews. Like, one value is going to be very high, like this. To alleviate this, a common way to handle attention scores just before computing them is to do a normalization. So here what we're doing is, after we calculate the product, we are going to divide it by the square root of the embedding size. The square root part is not important. It's just a factor of the embedding size. So if the embedding size was 100, we will be dividing all of the values by 10. If it was 256, we will divide all of the values by 16. And what that does is that it makes all of these values much smaller in scale, and thereby reduces those extreme numbers. So if I run this, see, now I have the embedding size is 100, but because I'm doing this normalization trick, you see that they're all pretty well spread out. Now, after the model starts to train, these numbers are going to shift, and we are going to show how those numbers shift, because that's what the model is going to learn about, how to give attention, about which words should give attention to which words when generating text. Anyway, so that was a little bit about the intuition behind what attention scores are. Now, let's talk about the concept of contextual embeddings. Now, suppose you have a query. It's just a string that says, "Yo dog, give me a badass underdog action movie." And suppose you have some keys, which are basically movies in your database, and each of those movies have an associated embeddings, as shown here with this orange boxes or yellow boxes. Now you have converted your queries into a query embedding vector, denoted here as Q. And then you have done your attention block, where you've basically taken the keys and the queries to generate Q.K-transpose. Basically that matml thing that we were talking about earlier, where Q is the query or the search embeddings, and K are the keys or the item embeddings. And with the softmax, you have arrived at a probability distribution, where each of the key has now been associated with a weight with which the query is relevant to that item. So in this case, because Die Hard is a badass underdog action movie, you have a high score, like a 0.84 score for Die Hard, and all of the rest also has good values. The Matrix is also an action movie, so it has 0.11 score. Now here you have the weightage across all of your key vectors. Now what if you wanted to combine them to form a new vector which captures the amount of context each item has given to the query? if you just do a weighted mean, which basically means that the embedding of Die Hard gets multiplied by 0.8, the embedding of Forrest Gump gets multiplied by 0.04, the matrix get multiplied by 0.11 and all that, and then those scaled vectors get summed together, basically to generate a new vector. That will be an aggregated key embedding. Given this query, you have aggregated all of the embeddings of your movie database and then generated a new embedding that has heavy bias on Die Hard because the query said that it needed a badass action movie. So this attention context vector has heavy sort of influence from Die Hard. If you change the query to something else, like give me a badass horror movie, then this final embedding will have a higher score for The Shining and lower score for all of the rest. And often we will also be adding the query embeddings with this context vector again to form a new contextual embedding, which basically uses both this key aggregate as well as the original query embedding to form a sort of contextual query vector. Because remember that this aggregated key embedding we have here is just a weighted average of the embeddings of the movies. It has actually no influence, like no direct influence from the query embeddings. All the query embedding did was tell how to average all these numbers. So when we add the query embedding back with the aggregated key embedding, you have a new numerical representation that is influenced by both the query as well as this aggregated key. And the last thing I'm going to talk about before jumping back into code is the concept of value embeddings. So value embeddings are generally also obtained from your keys. So your movie databases gets converted to a bunch of key embeddings through a neural network and also to value embeddings through another value neural network. And we're going to talk about these neural networks when we jump back into code. And the difference between having the separate key and value embedding is that you use the key embedding to compute this softmax operation to score each of the weightage values, and then you use the value embeddings to do this weighted mean operation where you are aggregating not from the key anymore, you're aggregating from the value. So what that does, it gives a more general model of combining these items with queries. So hopefully that sort of makes some sense. We are going to jump into code now to see how it all actually works under the hood. So here you have value embeddings, and again, if we run this, we have attention scores from key and value embeddings. We have the attention scores, which are 3, 1, and we have the value embeddings, which is of shape 3, 4, where 4 is the embedding size and 3 are the number of keys that we have. To do context embeddings, we are basically doing another matmul operation where we are taking attention scores and value embeddings and basically multiplying them. We are transposing the attention scores first so that from 3, 1 it becomes 1, 3, and when we do this product we have the shape of 1, 4, where we will basically be averaging all of those numbers. So let's break down how exactly these numbers have come. So you saw that the context embedding is minus 0.033.72. How are these numbers coming? Well, let's look at that. So attention score of key 0. That is this number, right? Let's sort of write it as that. And key 1 is this number. Let's write that too. And then for value embeddings, you have the value embedding of the first item as that. The value embedding of the next item is this. Now what we're going to do is multiply the first number with this entire vector, because this score determines how much of the first item to include in that aggregate score. So we're doing attention score key 0, which is this number, multiplied by value embedding 0, and then we're repeating it for this and that and this and that. And notice that these three numbers do add up to 1 because we did the softmax operation, right? Yeah, they do add up to 1 because we did that softmax. So if we did this, we receive these 3 new vectors, which are basically the scaled version of these value embeddings. And if we added all of these 3 vectors along the row, so this plus this plus this becomes the first element of that vector, we will have this vector, which is the same as this np.matmul operation we did at the beginning. So hopefully that sort of explains what happens when we are doing this attention multiplied by value embeddings. You're basically doing a weighted average. It's nothing more, nothing less. If the query wants to give the same attention, so in this case 0.333 attention score to each of the 3 items, is basically going to be a simple average. You're averaging the item embeddings. But what attention allows you to do is to find out how much these weights should be. So instead of just 0.3, 0.3, 0.3, you can choose to focus on specific items more, because like we saw in that Die Hard examples, depending on the query, you may want more information from a specific movie or a specific key. And the final thing here to do is to find context embedding, which is as simple as this. You add the context embedding here along with the original query embedding that came in. So that would give us a new embedding that is combining both the information from the original query as well as the information from the aggregation of the items. Hopefully that sort of explains what's going on under the hood with attention. In the next part of the video, we will discard NumPy and we will start with Pytorch, and we will implement a bare bones version of what transformer models look like. Let's go. But before that, if you haven't liked the video yet, go hit the like button. Subscribe to the channel because it helps us grow. We recently hit 10,000 subscribers on YouTube, and for me, that's a huge deal. And I want to continue to work on these videos because I have a lot of fun. If you've been a subscriber for this channel, I thank you. You guys are magnificent. Also magnificent are my Patreon supporters who help fund this channel, and I'm very grateful for all of your support. As a reminder, I will be uploading all of the code from this video, as well as all of the code, slides, everything that gets generated in this channel on that Patreon page. So if you want access to this code or any of the other files from any of my other videos, please go check out our Patreon. Thank you. So in the next part, we are basically going to take everything we did with NumPy and just converted into Pytorch, because with Pytorch we also have the ability to do backpropagation and basically train those query, key, and value networks to provide meaningful embedding representations. Basically, we have this calculate attention function which inputs the query, the keys, and the values. It performs the initial matrix multiplication between the query and the keys, and then it performs the softmax operation to get the normalized scores, and finally it does another matrix multiplication between the attention scores and the values. And hopefully everything we have discussed so far will make it easy for you to follow along what all happened here. And in the end, it returns the attention embedding, which is basically the aggregated values embeddings, and also the attention scores. And here I've run a simple experiment to show you how it works. So far you have seen that we have initialized the query and key embeddings as these 2D matrices, where you have the number of items and you have the embedding size. But starting now, we will introduce a batch dimension. Batch dimension basically means when you have several examples, instead of training each example one by one, you basically arrange them in a batch or in a stack and then compute all of them together on your GPU. We're going to see how exactly that works in a minute, but let's follow along what's happening here. Now here we have the batch size as 2, so when we do query dot shape, we see that the batch size is 2, the 4 is the number of queries, and 8 is the embedding size. And similarly, if we did key dot shape, it will be 2, 16, 8, because 16 is the number of keys. And then when we'll do the shape of the context vector, we'll see that it's 2, 4, 8, where 2 is the batch size, 4 is the number of queries, and 8 is the embedding size. So basically, for each query, you now have a context vector that summarizes all of the relevant key information. And for the attention scores, you have 2, 4, 16, which basically means for each query and each key, what is the attention score. So if I quickly print that out, this is a huge matrix. So let's say we just take attention score 0. This means for the first item in the batch, you have attention score of this. So if we take the first item of this, these are the attention scores of the first query. These are the attention score of the second query. And obviously, if we did the sum of this, this will convert to 1, because all of these values are the attention scores. First query gives to 16 different keys in our input. Anyway, now we have talked a lot about attention, but we haven't actually talked about attention yet, because everything we've done so far is just generated random numbers and just kind of shown the matrix multiplication of those two matrices. Now we are going to begin something more interesting, because now we are going to train on text. Specifically, we will be training a simple attention model to learn this sentence. Attention, we will train attention. Let's see how that works. So as usual with all types of NLP tasks, we first want to split these text into individual tokens. Now modern large language models use something called as a subword tokenizer, where you can basically split up words into smaller subwords and then use those subwords to represent a sequence. I have talked about this in my fine-tuned llama video, so if you want to check that out, please go do it. But because this is a very simple example, we are just going to use a simple word-based tokenization approach. So given that, we will first split the text. So what that will do is it will just split this text into individual words, and then we will create a vocabulary of the words in our sequence. So if we run that, we'll find that we have 1, 2, 3, 4, 5, 6 total entries there that contain these different values. Now this is of shape 1,7, and we will convert this string into an integer based representation where the first 3 is basically attention, because you see that the index of the word attention is set to 3. The next 2 is this exclamation mark. Then we have we, which is 4, and then will, which is 0, and so on. So you have a sequence of length 7. The next thing we will do is to convert these integer indexes into vector embeddings. Now, these vector embeddings are kind of similar to the original vector embeddings that we started with. We originally set some arbitrary values here, and now as well, we will start with arbitrary float values, but we will train the model to learn the correct values. Let's see how to do that. The easiest way to do that is to train what's called an embedding layer. In Pytorch, you define it using torch.nn.embedding, and you pass in the number of embeddings you want to train. In this case, since our vocabulary has six different tokens, we want to train 6 different embeddings, 1 for each token. And the embedding dimension is a hyperparameter that we decide, which basically states how many attributes do you want to train per token. And if we do embedding layer.weight, you'll basically see what it did. It basically created this matrix of shape 6,8. If you do the shape of this guy, you'll see indeed it is 6,8, where 6 is the length of our vocabulary and 8 is the embedding size that we had set. It's kind of a lookup table where the first index refers to the word will, because it's at the first index. The fourth index, attention :3, is basically 0, 1, 2, 3. This vector represents the word attention. And another important thing is this requires grad equal to true, which basically suggests that in the future, we will be using gradients to tune these values so that they optimize for a loss function. I'm going to show exactly what that means in a moment. So if we pass our integer tokens, which is this 3, 2, 4, 0, 5, 3, 1, through the embeddings, and then show what it looks like, you basically have a new sort of a matrix. And if you did the shape of this will be 1,7,8. The 1 is again the batch dimension. The 7 is the length of the sequence. This 3, 2, 4, 0, 5, 3, 1. This attention, we will train attention, full stop. This whole thing has 7 tokens, so that's why you have 7, which is the sequence length, and 8 is the size of the embeddings from our embedding layer. Not only that, let's see what values these are. The first one is this 1.3968 that ends with 0.562. Well, this is this index. These indexes 0, 1, 2, 3. The third thing, which is basically attention, which is the first word. So that's why in the embeddings, the first row is the third embedding, which is corresponding to attention. The next one is the embedding corresponding to the exclamation mark. Next one is we. Next one is will. So if you just pause and rewind and convince yourself of that. For example, the word will is this one, which is here at the very top, and in our vocab dictionary it was 0 index, meaning at the very top. Now, in the previous examples, we used a query vector, a key vector, and a value vector. And I also said that the key and the value vectors come from the item embeddings, and the query vector comes from the search query. Now, here's where this gets interesting. We will be using something called as self-attention. What self-attention basically means is that the query, the key, and the value vector all come from the same source. What that basically means is that now that we have these embeddings, these 7 embeddings of shape 8 each, which represents each word in our input sentence, we are going to use them as a query as well as the key as well as the value. What does that mean? Well, what that means is that you're basically learning how much attention each word is providing to every other word in the sequence, because you're effectively treating each word as a search query, and you're treating every other word in the sequence as the key or the value item embeddings. So the way to do this is we will train some sort of a neural network. Here I've just used a linear layer, but in the future we will be using a non-linear layer. And so what we have done here is, after we pass our integer tokens through the embedding layer, we pass those same embeddings through the query layer, the key layer, and the dense layer. And what ends up happening is that you get a query matrix, a key matrix, and a value matrix. And they are all of shape 1, 7, 8, where again 7 is the sequence length, 8 is the embedding size. And finally, we will use our famous calculate attention function, which will compute the attention context vector as well as the attention scores. And indeed, it does that. And here, if you see the attention scores, this basically suggests how much attention each word has provided to every other word in the sentence. Now, there are a couple of issues. The most important of these issues are that we want to train a language model that can generate tokens. And how these models work is that they input a token, then they predict the next word. Then this next word gets inputted back into the model as a new sequence, and then that generates a new word. And that word again gets passed into the model as an extended sequence, and so on and so forth. They generate the entire sentence. Every new word depends only on the words that came before it. When you're generating, say, the third word in the sequence, it's only dependent on the first 2 words. The next 10 words have not yet been generated yet, so you can't condition the generation of the third word on the 4th, 5th, 6th, or 7th word. But here, we are asking the model to provide attention to every word. So the first word, which is this first value, is providing attention to the first word, the second word, the third word. That's not possible, because when we're going to do inference on this model and generate new words, we won't have access to these words at all. Well, here's a trick. We will use a right triangular matrix. A right triangular matrix basically looks like this. You have a bunch of ones this side of the diagonal, and on the other side of the diagonal, everything is 0. What that basically means is that this is a mask that tells every token which other token you can provide attention to, and which tokens are out of your bounds. So for the first row, you only have the first token as 1, meaning that this position, you can only provide attention to the first input. And similarly for the third one, you can't provide attention to anything from 4, 5, 6, or 7. And inside our calculate attention function, we have renamed it as calculate masked attention, which now also inputs this mask. And the only change is that now we are explicitly setting the attention score of the indices, which are 0 here, to minus 10 to the 9, which is like a really high negative number. So just before you run softmax, you just set this number to extremely low. And what that'll do is, when we run softmax, it will convert those very low numbers to 0. Let's see that in action. We have that. Now we will run this. We'll run this, and again, the shapes and all are cool. But if we print out the attention scores now, you'll see that now everything here is 0. It's like a right triangle where everything that we set here is 0. Because you're applying it before softmax, all of the non-zero values still add up to 1. So the third index does have the attention scores of the input at token 0, token 1, and token 2, and they all still add up to 1. Okay, so that is about all we need to actually write one decoder transformer block. Everything that a decoder transformer block does is right there on this notebook. You take some input embeddings, you convert them to key, query, and value embeddings, then you apply the causal mask attention. So the only thing remaining is to bring all of this together and just write a transformer decoder model, and then train it on some wacky sequence to see if it actually learns this sequence. For this, we have this new notebook where I'll quickly go over what the code sort of looks like. So first up, we have this attention layer, and all this attention layer does is it has a query, key, and a dense linear projection matrices which convert the input embeddings into the query, keys, and values, and then uses the mask attention thing where it passes the key, query, and the value as well as the right triangular mask to calculate the attention. And then we have the transformer block, which basically uses this attention layer to do more processing. Basically, in the transformer block, you just have one attention layer. You have a feed-forward neural network, which is basically like a simple network I've written here, which inputs x, passes it through a linear layer, applies a nonlinear function and passes it through another linear layer and outputs it. And finally, you have a layer norm, which basically normalizes the output so as to not introduce any drift if you have a very long transformer network. And inside the forward function, you basically apply the attention layer, which again is this query key value and the calculate mask attention thingy. Then you apply the layer norm, then you apply the feed forward network, and you applied another nonlinear function, and finally you add back the original X back to the context. This is that residual connection that I was talking about a little while back. And finally, we have a transformer, which is basically a collection of these transformer blocks stacked on top of each other. So here you have a module list where you have a list of this transformer blocks. So if you have num layers equal to 3, it means you have 3 transformer blocks. All that it does, in the forward function, is it just loops over these transformer blocks and just passes the input one by one. These transformer blocks all get applied sequentially, one after the other. But the main point of attention mechanisms is this calculate mask attention function. This computes the query key values parallelly. So every token parallelly computes the attention scores and the context vectors for every other token previous to it, parallelly in one shot. Everything is simultaneously processing at the same time, and that is the magic of transformers. The last piece of the puzzle, however, is how to model positions. Remember, when we aggregated those key embeddings, we did not have any notion of sequence. We don't care if Die Hard was the second movie in the database or the fourth movie in the database. Its order in the sequence does not matter. But with text and these text tokens, the orders do matter. So to do this, we train what is called a positional encoding. Positional encodings are trained for each position in the sequence. There's a specific position encoding for position 0, specific one for position 1, 2, and so on. And the way we will do it is that after we compute the word embedding of a specific token, we will just simply add these positional encodings onto the word embedding to get this new word positional pair embedding, and this gets passed through the attention layers. That's how transformers model sequences. The notion of ordering comes entirely from the positional embeddings themselves. Let's see how to define it. Well, the most classic way to do it is using sinusoidal positional encodings. You can basically imagine these positional encodings as yet another lookup table, like the word embeddings lookup table. See, the word embeddings lookup table were there to look up the embeddings for each word. The positional encodings are there to look up the embedding for each position. So if you want to train a language model with a max sequence length of say 200, you will train 200 vectors to represent each of those positions. And one way to do this is this sinusoidal positional encoding, where every embedding is a high order sinusoidal function. And finally, we have the Causal Language Model class, which basically encapsulates everything. It has a transformer, which I should have called a decoder transformer. Not really, it's not really a transformer, it's a transformer decoder, but I don't want to introduce bugs right now, so I'm just going to keep it as a transformer. It's not a transformer, it's a transformer decoder. And we have sinusoidal positional encodings, and when we receive X, which in this case are going to be integer token sequences, we'll first convert them into an embedding, then we'll add the positional encoding on top of the word embeddings, and then we'll pass it through the transformer, which will apply these transformer blocks one after the other, and after that finishes processing, we will finally convert these embeddings back to a probability distribution between the number of words. So the output will be a probability for each word, and to do that we will basically just do another matrix multiplication operation using the embedding layer. Okay, so it definitely works, and if you see what the output is, it's basically this unnormalized values for each word in the vocabulary. So here I had defined the vocabulary size as 5, so that's why you have these 5 values, which are unnormalized logits. And if we do a softmax on this, we'll find the probability of each word that the network currently predicts. Let's take this toy dataset and see if we can train our transformer model, and then let's see if we can train our causal language model to learn each of these sequences. Here I have written some facts like you shouldn't forget to like, share, and subscribe, and don't forget that machine learning is fun. And here I've added some special tokens, pat, start, and end. I'm going to talk about that in a bit. And then we have a vocabulary of size 20 that contains all of the words that are in our dataset. Now, again, in general, we use subword tokenizers when we train real language models, but this is a demonstration. So I'm just using a simple word tokenizer, and I'm using every word in the vocabulary. Next, we have some helper functions to encode, which basically will input a string and then output that list of integer tokens. This is the converted integer tokenized representation of that data set. And if I take the first value of this and run decode on this, all I've done is appended it with the start token, and in the end we have an end token, and we have a pat token here because the maximum size sequence is this one, and we want this tensor to be rectangular. And the reason to add this start token will be apparent when I talk about inferencing in a bit. Basically, when no sentence exists, we need to generate the first word or the first token, right? That's when we will input the start token into the model so that the model outputs the first token, and then we will pass that token back into the model to generate the rest of the sentence. And the function of the end token is that if the model ever predicts the end token, we stop the prediction generation right there. We don't need to proceed any further because the model thinks that's where the sentence ends. So that's the significance of the start, end, and the pat token. Now, the way to train causal language models is that you train it on next word prediction. And because we have already discussed that, because we have already discussed that each word only provides attention to everything that came before it, we can train on entire sequences parallelly. So the input to the model is going to be start, if you like machine learning, I like you, and the output would be, if you like machine learning, I like you, end. Basically shift it to the right by 1. The corresponding output of start, we will try to fit it to if. The corresponding output of start if, we will try to fit it to you. The corresponding word of start if you, will try to fit it to like, and so on. That's how we will try to fit the model to do that. So here I have shown how the input tokens and the target tokens is going to look like. The input sequence is this, and the output sequence is basically shifted by 1. So 1 4 16 7 becomes 4 16 7 14. And here I have again shown the same example, but as strings, so that it's more easier to follow what's going on. Finally, the only thing remaining to train the model is to define a loss function. Well, to define a loss function, let's input some tokens into our causal language models. Now we have the logits. So the shape is 5, which is the batch size because we had 5 input strings here. And then we have 9, which is basically the sequence length, 3, 4, 5, 6, 7, 8, 9. And this 20 is the size of our vocabulary. So if I did logits of 0, which means for the first example, for 2, which means for the second token we need to generate, we have this, which is basically what the unnormalized logits are for each of these tokens. So if we pass this through a softmax, we will find the probability of every token as the model suggests right now at its untrained state, right? So here we see that what the probability the model has assigned to each word in the vocabulary. Obviously, these values don't mean anything because the model has not yet been trained yet. To train it, we first need the loss function. The first thing we will do is we will flatten all of this. So from 5, 9, 20, we become 45, 20, which means we are just arranging it in 2D matrix, and we are doing it the same for our target tokens because these are the ground truth that we had obtained from our dataset. And by doing this, what we are essentially doing is we are flattening it all out. We have this flattened labels, and for each index we have a probability distribution, and so we can apply the cross entropy loss to learn to fit this. So let's print the loss. It says it's 6, which is basically how far away the current prediction are with our ground truth response. So if we ran this thing and let's say we printed the loss, so it starts at 6. If we ran this again, well, now it's 5.9. If we ran it again and again and again and again, you see it's continuously going lower and going lower. That's what training does. It makes the loss go lower. So if we just run this in a loop and we see that the loss indeed is going lower and lower, all that is doing here is this loss or backward is computing the backpropagation loss for every parameter, every trainable parameter in our network. All of those feed forward layers that we had, all of those query, key, and dense linear layers we had, and of course the word embeddings as well. Now the positional encodings are actually kept as constant in this example, but everything else, they're all getting trained as the loss is getting lower and lower. And finally, if we, after training the model, if we showed what the logits are, and we did an argmax, meaning we are finding the most probable values, we see that it's beginning to look very similar to our target sequence. Now obviously our model always predicts the first token as 4, which I think, if I remember correctly, 4 is don't. And the reason it predicts don't is because in our data set we had 2 instances where the sentence started with don't. So that was the predominant word that was getting generated in the first token after you input start. So obviously there is no randomness here because we are using argmax. So that's why it has learned to predict 4 whenever you input start. So here I have an input string which is start, and then I convert it into the integer token, and then I pass that token through the language model, take the probability of the model by doing the softmax, and then do an argmax to find the index of the highest logit in the output, and then finally we append it back to the new sequence. So when we input start, the new token output is don't with a 26.21% confidence, which is not very high, and the new sequence is start don't. And so if I just for now just copy this here and run it again, you see the new word is forget, and if I run that again, the new word is machine, where the model is trying to predict this particular sentence right now. Another cool thing we can do with these attention scores that gets generated as these models get predicted is to display how they look like. Maybe I should use a smaller. So for example, while predicting the word machine, it's looking at don't and forget, and when you input don't forget machine, it to predict learning, in the last layer it gives a lot of attention to the word machine. I guess it uses that to generate the next word. So these are interesting things in my opinion. Now also you can write all of that inside a single loop. Here I have a function called generation, which basically passes in the input tokens one by one, appends to the sentence, and then keeps producing words until it hits the end token. So if I if I input the word I like, it predicts start I like you more than machine learning, which indeed is one of the sentences in our data set right there. So hopefully that was fun, and I hope you learned something about language models and Pytorch and everything we talked about today. Please do let us know in the comments what your feedback is about videos like these. Again, thanks a lot for helping me reach 10,000 subscribers. I'm very excited for the future. All my friends in India, wish you a very happy Diwali, and for all my friends in the US, happy Halloween.